Well, class, welcome back to take 2 of today's lesson. In order to see where we're going with today's lesson, I wanted to start with going back to some prior information. And we're going to begin with drawing the vertical line x equals -3. When I draw, I'm on there. When we draw the line, vertical line, x equals -3, gonna look like this. And we're gonna plot this point, 3, 0. And our task is to sketch all of the points, so the collection of points that are equidistant from this line and this point. Now, if we start with, obviously one of our main ones would be this point right here. We can see that this center point, the origin, is 3 units away from that point. It's also 3 units away from that line. But we want to plot all of the points that are equidistant between these two. If I tried to plot this point, for example, we can see that this point is, again, only 3 units away from the line. But based on the fact that this is a hypotenuse of a triangle, it's definitely going to be further away from that point than it is from that line. So the only thing that we could do would be to take this point, and if we tried to, I guess that's not going to work. I'm just going to replot it. We could maybe slide this point over a little bit, and we could try to come up with a point that is going to be more equidistant. So if I erase these, and again, just kind of move this point around, this may not be a very good, let's try this again here. Maybe if we plotted the point just kind of off to here a little bit, now it might be more equidistant between these two. And then let's say we plotted another point over here. So this one, if we're looking at the distances here, we want to try to make sure that those distances are staying the same. And obviously, we could plot some points down on the lower half of the graph, maybe over here, maybe over here. What we should ultimately see is that these points end up forming a parabola. And this right here gives us a much more official definition of what a parabola is. Now, today's goal, or this next unit, is going to be looking at all these different conic sections. And as you can see, a parabola here is one type of conic section. A conic section is simply the result of the intersection of these two right circular cones and then some sort of a plane. We've already talked about circles back in our polar units. We know that circles have an equation that looks something like this, where the r is actually the radius of the circle. And we've seen parabolas before. We've graphed parabolas back in Algebra 2 even. We've seen parabolas that look like this, y equals x squared. We could have parabolas that say y equals -x squared. We're going to be looking at parabolas again in a little bit more detail, however. We're also going to be talking about ellipses and hyperbolas. You'll notice that hyperbolas almost look like two parabolas that are opposite of each other. So we're going to have this one down here, and then of course we're going to have this one up here as well. Now, in real life, we talk about some of these different conic sections. They seem like something very mathematical, something that we're never going to use in real life. But in reality, conics are actually very commonly used. For example, we're all familiar with seeing satellite dishes, telescopes. These are all taking the form of a parabola. And we can actually use some of the characteristics of these parabolas to find out some key information here. Ellipses, these are very common in the planetary orbits. And hyperbolas, I think, is interesting. We can actually use hyperbolas to identify exactly where a lightning might strike. Now, today's focus, guys, is going to be on parabolas. And that definition that I showed you up above is our true definition of a parabola. The parabola is the set of all points in a plane that are the same distance from a fixed point, the focus, and a fixed line, the directrix. So if you think back to the example that we did above, we plotted that fixed line. This was what we called the directrix. We plotted a point. This was what we called the focus. And then we identified all of the points that were equidistant between those, and there was our parabola. So a few key things about the parabolas. Okay, again, we've worked with parabolas before. We've seen parabolas that open up and down, like the two that we see in front of us. The parabolas that we're going to be dealing with today are going to have a vertex at the origin. That vertex will eventually move, but today we're going to focus on just the basics. When the vertex is at the origin and the parabola is opening up and down, then it's going to have an axis of symmetry of the y-axis. Now keep in mind, here's my axis of symmetry. An axis of symmetry is the line that basically divides the parabola into two halves. If you fold it on that line, the two halves are going to match. One thing to remember is that if your parabola opens up and down, the axis of symmetry will always be a vertical line. Okay, now we've seen these parabolas before. I do want to focus on these two new aspects, the focus and the directrix. Notice where they are. In both diagrams, the focus is the point that is inside. So first of all, it is a point and it is inside the parabola. You'll also notice that the directrix is a line, okay, and it is always outside the parabola. Now look at where that directrix and that line are located. As we said, they have to be, the points on the parabola are equidistant between those 2 points. So if you look at your origin, which is where our vertex is, we can see that the distance from the vertex to that focus is a units. And the distance from the vertex to that line is also a units. That a is right there in the equation. Also notice that, just like we've seen with parabolas in the past, if this part of the equation is positive, then the parabola opens up. If this part of the equation is negative, then the parabola is going to open down. And the last thing I want you to notice is the rest of the equation. Parabolas that open down are going to have a y and an x squared. Now, you guys are used to seeing parabolas or equations written in this form, y equals x squared. All we're doing is flipping things around a little bit here. It's still the same key things. If you see a y and x squared, you know that you have a parabola that opens either up or down. Okay? I also wanted to emphasize again, adding on to some of our little notes down here at the bottom, let's talk for one more second about that a value in the equation. As we see in the diagram above, the a value is actually the distance from the vertex to the focus, and it's also the distance from the vertex to the directrix. So it's giving us that common distance. Now, the one thing we haven't talked about so far this year really are parabolas that open left and right. Parabolas that open left and right, a few distinctions. First of all, I want you to notice that in a parabolas open left and right, we have x and we have y squared versus the other way around. The rest of the equations really do stay the same. We still have this 4a in both equations. If it's positive, it opens to the right. If it's negative, it opens to the left. That a value is still the distance from the vertex to the focus and from the vertex to the directrix. That's still going to be our a value. When our graph opens left and right, it's important to note that the axis of symmetry will always be horizontal. And these are all details and characteristics of the graph that we're going to be able to look at to help us when we're actually graphing some of these functions. Okay, so now, we have three, actually let's do this first. We have a couple of main goals here for today. Your goals are that I want you to be able to write an equation of a parabola given key information about the parabola. I want you to be able to graph a parabola with a good a reasonable amount of accuracy. And I want you to be able to evaluate different characteristics of the parabola. Okay, so as we look at this first example, our job here, I'm just sorry, I apologize, that wasn't scribbled out. Okay, so in our first example, I want you to write the equation of the parabola. We're going to identify the focus and the directrix, so these new key parts, and we're going to sketch the graph. Okay, now some of the information is given. We know that the vertex is at 0, 0, so I'll plot that point. And we are given the focus at 6, 0. So the focus is going to be right over here. Focus and vertex. Now remember the key things that we need. We need to write the equation. we need to identify the focus. We need to identify the directrix. The focus right away, that's given. Okay, now a couple of things that we know. We know that the focus is always inside the parabola. And therefore, based on the position of these two, we know that the parabola has to be opening to the right. Okay, so again, look for that key detail. Because the parabola is opening to the right, it's going to have to follow the format of x squared. Oops, I apologize. It's going to have to follow the format of y squared equals either positive or negative 4ax. Remember, parabolas that open left and right have a y squared. Parabolas that open up and down have an x squared. Now, because it's opening to the right, we know that this is going to have to be positive, so I can kind of limit my equation to this at this point. Next thing would be look at the distance between the vertex and the focus. The distance here is 6. Remember that that's your a value. So now I can go back to this equation and I can plug 6 in for my a value. Now my equation says this, y squared equals 24x. So my first task was to write the equation y squared equals 24x of the parabola. I've already identified the focus. Now I need the directrix. Remember the directrix, is a line. So we're going to have to write an equation. We also remember that the directrix is always outside the parabola, and it is the same distance from the vertex as the focus. So if we go 6 units the other direction, that should be our directrix. Because this is a vertical line, we're going to be writing the equation x equals -6. So we've done everything in terms of writing the equation, the focus, the directrix, and we have a very rough estimate of this sketch. But I want to go back and make sure that our sketches are a little bit more detailed. So I'm going to erase the parabola that I drew, and we're going to try to come up with a way to be a little bit more accurate with this. Since we already have an equation that we could use, what we can do is take this equation and simply create a very simple table and plug in a couple of different x values and come up with some y values and plot the points. Now I'm going to use the x value of 6, just because that's our focus point, which we've already kind of said is kind of a key point. So if I plug in an x value of 6, my equation is y squared equals 24 times 6. Y squared is 144, and when I take the square root, y could be positive or -12, which means I technically have 2 different points that I could plot here. I could plot the point 6, +12 way up here, and 6, -12 way down here. Here's my vertex, and now I can sketch in this parabola. As you can see, this parabola is quite a bit wider than my original sketch. That's why we need to be accurate. Now I want to talk a little bit more about these points that we just plotted here. If you look at the distance between those 2 points, if this point was at -12 and this point was at +12, the distance between these is 24. Notice that that's the same value that was in our equation. This distance is what we refer to as the focal width, and it's a quick way that we can actually graph these a little bit more accurately and also a little bit faster. So let's talk for just a quick minute about that focal width. Now, I will tell you the official name for this is the latus rectum. Yes, we said rectum, and that's why we generally use the word focal width, because it just sounds a little bit nicer. The focal width is just the segment that joins the 2 points on the parabola that are either directly above and below the focus or directly to the right and left of the focus. The total length of this focal width is always 4a, and that's that value in the equation. Okay, so for example, if I'm graphing any parabola here, and let's say we drew in this parabola, and my focus was right here. This segment that goes from here straight through the focus to here, this is what we're calling the focal width, and this is always 4a units. So we're going to add that detail on as we graph, as we look at one more example here. Once again, our goals are the same. We want to be able to write the equation, identify the focus and the directrix, and we want to sketch an accurate graph. And when we sketch that graph, this time we're also going to use focal width to help us be very accurate with the graph. So the vertex again is at 0, 0. This time I'm giving you the directrix, which is the horizontal line, y equals -3, so we'll plot that line. And if you look for the distance between the vertex and the directrix, we notice that that's a distance of 3, and that distance is the A value. Now, based on where these are positioned, since we know that the directrix has to be outside the parabola, we know that this parabola has to be opening in the upward direction. Okay? If the parabola is opening up, then we know it has to be in the form of x squared equals positive 4ay. Now, we just established that our a value was 3. So if I plug that a value of 3 in, I now have this equation which says x squared equals 12y. So step 1 is done. We have our equation. Okay, from this equation, we need to identify the focus and the directrix. The directrix was given, y equals -3. The focus, remember, this is going to be a point, and it has to be inside the parabola. And it has to be the same distance away as the directrix. So if we go 3 units the other direction, there's my focus, and that's at the point 0, 3. So now I've got my equation, my focus, my directrix. Now I need my graph. Now I started out with a very general sketch just to kind of help me see the direction, but now is where the accuracy comes in. So we're going to talk for a minute here about focal width. Okay, remember the focal width is the distance, the segment that goes through the through the focus and connects the two sides of the parabola. The focal width is always 4a units long. Well, in our problem, 4a is actually this value of 12. So that means our focal width is going to be 12 units long. Now, when I'm plotting my focal width, remember it has to go through the focus. So that means I need to divide this by 2, and I'm going to have to go 6 units each direction from the focus. So from my focus points, I'm going to go 6 units to the right. I'm going to go 6 units to the left. That's a total of 12 units. There's my vertex. And now I can sketch in my parabola, and I have that width accurately. Okay? Sorry. Okay, in our next example, this time I'm wanting you to write the equation of the parabola. It doesn't necessarily say to graph it, although we're probably going to need to see the graph to help us write the equation a little bit. So again, the vertex here is given. The vertex is at 0, 0. We know that the axis of symmetry is the x-axis. So let's think about what that tells us. If the axis of symmetry is the x-axis, anytime the axis of symmetry is horizontal, that means that the graph is going to open either left or right. So we're basically dealing with a parabola that either does this or it does this. We haven't decided which one yet. But because we know that it's either left or right, we know that it has to take the form of x squared equals, has to take the form of y squared, either positive or negative, 4ax. Okay, now how do we decide if it's left or right? That's where this next piece of information comes in. They've given us one point that's actually on the parabola. So if I plot that point, and I'm going to erase these kind of estimated little parabolas here. If I plot this point 4, 6, because of where that point is located and it's on the parabola, that tells me that my parabola has to be opening up toward the right. I can also plot a symmetric point down here at 4, -6, and I can actually see a really good graph, a really good picture here of the parabola. Now, let's talk about the missing part of this equation. What we still don't know is the a value. In past examples, I gave you the focus or the directrix. And we can use the focus and the directrix to help us get the A value. But in this example, I didn't give you either one of these pieces of information. The only thing I gave you was the 0.46. Because this is an X and a Y value, we can actually plug those values into the equation, plug in the 4 for the X, and we can actually use this equation to solve for the A value. Now, one thing that we didn't say a second ago that I want to add in, okay, we're going to solve for A. Because we know that this equation now opens to the right, we know that it has to be a positive here because it opens to the right. So if I solve this equation, 36 equals 16A, my A value is 2.25. And remember, my goal here was to be able to write the actually write the equation. So once I know my A value, if I go back up and plug it in, my equation is actually y squared equals positive 4 times my A value times x. And therefore, that would be y squared equals 9x. And there's my equation. One of the key points I want you to take away from this is, if you know a point on the parabola, you can substitute that point in, for x and y, and you can use that to solve for the A value. You are, however, still going to have to pay attention to clues, so you're still going to have to use clues to tell you the direction of the graph so that you know which equation to pick, because that direction is going to be key to help you determine whether or not you should be doing y squared equals 4ax, or should you be doing x squared equals 4ay. So pay attention as you're trying some of these problems here, guys. Really pay attention to clues that are going to tell you about the direction so that you know which equation to work with. Okay, a couple more little examples and we're going to put it all together. A lot of the problems you're going to be doing are going to be asking for the following pieces of information. This time I'm actually giving you the equation. You don't need to write it. You need to identify the vertex, the focus, the directrix, and I'm going to ask for 2 other points that are determining the focal width of the parabola. And then with all that key information, we're going to sketch a graph. So this time you have the equation. We need the vertex, the focus, the directrix, and we need 2 points that form the focal width. So I'm going to right away go ahead and jot in those ordered pairs so that I remember I need those. Now, I did tell you that in all the problems we're doing today, our vertex is going to be at 0, 0. That's going to change tomorrow, and you're going to see it in the equations. But for today, I'm letting you know these have a vertex at 0, 0. So we can plot that. Now, how are we going to figure out where the focus and the directrix are? In order to figure out the focus and the directrix, we're going to need to know the A value. So if you look back at the equation, remember that 16 is actually representing our 4A, which means our A value has to be 4. Now, based on the equation itself, remember I said you always have to pay attention to direction. Based on the equation, since our equation has y squared and x, we know that this equation is going to open either left or right, okay? But because this is a positive, we know it's going to have to open up to the right. So let's think about how we can put all of this together. If we know the A value is 4, and we know that the parabola is opening to the right, then that means that the focus, which is inside the parabola, is going to be 4 units to the right. There's my focus, and that point is going to be at 4, 0. And I know my directrix is going to be 4 units to the other direction, so my directrix is going to be over here at x equals -4. Remember, the focus is a point and the directrix is a line. So make sure you're writing an equation for that one. Okay, for the focal width, remember that the focal width is always the 4A value. In this case, that 4A value is 16. Now that means that we need to go 8 units each direction from the focus. Okay, and I'm emphasizing, how to use that focal width here. So from my focus point, I'm going to go 8 units up, I'm going to go 8 units down, and there's my parabola. Now over here, I do want you to identify those 2 points you plotted. So if you look at this point was at 4, +8, and this point was at 4, -8. So there's these 2 points that we have for our the ends of our focal width. So here's the key information when we are sketching our graphs, the key information that we're going to be looking for. And remember how to use the equation to be able to actually come up with those A values. One last example just to make sure we have the idea here. Okay, same things. We need the vertex, the focus, the directrix. So vertex, focus, directrix. We also need 2 points that form the focal width. So I'm going to write focal width, and we're going to need 2 points here. And we have the equation. So as we look at the equation, let's first talk about the direction. Okay, based on this equation having an x squared and a y, we know that this graph is going to either open up or down. And because this is negative, we know that it's actually going to be opening down. I did say that all of these equations today have a vertex at 0, 0, so we can plot that point, and we know it's going down. Now, for the focus and the directrix, we need the A value. So if we look at that 12, remember that that 12 is actually representing 4A, which means our A value is 3. What that means is that the focus and the directrix are 3 units away from the vertex. So at this vertex, if I go down 3 units, there's my focus. And if I go up 3 units, there's my directrix. And remember, we know that the focus has to be down 3 units because the focus has to be inside the parabola and the parabola is opening down. So if we identify these, my focus is at 0, -3. My directrix is the line y equals +3. Last thing I need then is my focal width. We know that the focal width is 4A units, and we know that 4A in this case is 12. And we know that that means we have to divide that in half and go 6 units each direction from the vertex. Or, I'm sorry, from the focus. Apologize here. So if we go back to my focus and I go 6 units to the right and I go 6 units to the left, there's my vertex, and there's the sketch of my parabola. The focal points here, the focal width points, were at 6, -3, and over here at -6, -3. So those -6, -3, and +6, -3. Here's my key information about my graph. Okay. Key points to remember. That A value that's in the 4A in the equation, remember that that tells you the distance from the vertex to the focus and from the vertex to the directrix. Remember that the 4A value in the equation, that is your focal width. Okay, so that's that distance between the 2 ends of the parabola through the focus point. We need to pay attention to direction. So equations that have a y squared and the 4ax, these are equations that are going to open either right or left. If your equation is x squared and 4ay, these are going to open either up or down. So always pay attention to that. Remember that your focus has to be inside your parabola, and your directrix has to be outside the parabola. And then the last detail I wanted to remind you of is if you are given a point on the parabola itself, Remember, the focus is not on the parabola. It's outside or it's inside the parabola. But if you're given a point on the parabola, you can use that point and substitute in for x and y and then solve for your a value. And again, once you know your a value, then you can use that value to plot your focus, your directrix. You can use it for your focal width. So that a value is key. Okay. When you're working on your My Math Lab, take your time, really look at some of these key pieces of information. Try to use this almost as a little cheat sheet to help you through some of those problems. And good luck.